This is section 5.3b, solving trigonometric equations. The first thing, of course, to remind you is that you have to get out your unit circle. Just as in the last lesson, most of this lesson depends on the unit circle, and so that's going to be your best buddy for this lesson. You want to have it right next to you. Let's look at the first example. So today we are going to continue solving trigonometric equations, but we're going to look at a couple of different cases that we haven't really seen yet. For example, cosine x plus 1 equals sine x. Now, when you look at this, you're trying to solve for x, but it's not that easy, as you can see, because you've got two different trig functions, and it's not clear how to proceed. So this is the technique that you're going to learn today, one of the techniques. Square both sides, then check each solution in the original equation. All right, just to explain that a little bit, the reason for squaring both sides is because sometimes when you have a trig equation, if you square both sides, you can end up with something that will look like one of the Pythagorean identities. You know, sine squared x plus cosine squared x equals 1, or 1 plus tangent squared x equals secant squared x, or 1 plus cotangent squared x equals cosecant squared x. All right, so these are the Pythagorean identities, and so squaring both sides will help us to perhaps use one of those. Now, you don't always know when you have a trig equation whether it's going to work or not, but at least it's worth a try. The next part is a little less intuitive, checking each solution in the original equation. And the reason you have to do this is when you square both sides, you're introducing a possible discrepancy in sign. And all I mean by that is, you know, when you square a negative, you end up with a positive. And since you're kind of artificially squaring both sides here, you do have to check it in the original equation, because the original equation isn't the equation with both sides squared. It's with both sides unsquared. And that's why the sign differences that the squaring introduces can sometimes introduce what they call extraneous solutions. That is, angles that seem to be the solution for this equation but actually aren't. And the only way you can find that out is by testing whatever answer you get in the original equation. Alright, so with this example, I'm just going to walk you through it step by step, and then on the next screen you'll have a chance to do one on your own. So we square both sides, and we end up with cosine squared x plus 2 cosine x plus 1 equals sine squared x. Now you'll recognize that we've got two terms that have cosine in it and one term that has sine in it, sine squared. And this is where we want to use our Pythagorean identity. So cosine squared x plus 2 cosine x plus 1 equals 1 minus cosine squared x. Sine squared is simply 1 minus cosine squared x because of one of the Pythagorean identities. Now we're just going to do a bunch of combining like terms, right? So 2 cosine squared x plus 2 cosine x equals 0. We just put whatever was on the right side of the equation to the left. That gives us 0 on the right, and now we can proceed as we normally would with the quadratic equation. So we factor out the 2 cosine x, and we have 2 cosine x times the quantity cosine x plus 1 equals 0. And then that means that our two options are 2 cosine x equals 0 or cosine x plus 1 equals 0. Cosine x equals 0 on the left side. That's just because we divided both sides by 2, and we end up just with cosine x equals 0. And on the right side, we simply move the 1 over, and we have cosine x equals negative 1. Now, this is where you want to consult your unit circle. Remember that on your unit circle, the x-coordinates of points that are on the circle represent the cosines of the corresponding angles. So look on the unit circle for where you see an x-coordinate of 0. Alright, so you should have found that on your unit circle you have x-coordinates of 0 at the angles pi over 2 and 3 pi over 2. And also using the unit circle for finding an x-coordinate of negative 1, the only place where that happens is x equals pi. Alright, so it appears that we have three solutions to this equation, but this is where you need to be careful. if you square both sides, you have to check each solution in the original because you may end up with an extraneous solution, a solution that is invalid. So let's test them one by one. First, let's test pi over 2. All right, we're going to simply take this solution pi over 2, and we're going to plug it in for x in our original equation. Okay, so we're going to go up here to the top. We're going to circle that original equation in red because we want to make sure that we're using that for checking our solutions. And into this circled equation, we are now going to plug in pi over 2 for x. So does it work? Well, turns out that it does. Cosine pi over 2, that is cosine of 90. You can see that on your unit circles. The cosine of pi over 2 is 0, and 0 plus 1 is 1. The sine of pi over 2 is 1, and therefore 1 equals 1. And so pi over 2 is a solution. It is a solution. And if you want, you can circle it just to keep track of the solutions that are valid. Now, let's look at 3 pi over 2. Does 3 pi over 2 work? Well, what's the cosine of 3 pi over 2? You can find that on your unit circle. And you'll see that the cosine of 3 pi over 2 is 0. So we have 0 plus 1. But the sine of 3 pi over 2, the sine of 3 pi over 2 is negative 1. And 1 is not equal to negative 1. Therefore, 3 pi over 2 is an extraneous solution. And we're going to put a big fat red X through it. All right, and finally we need to test x equals pi. Make sure that works. So we're going to plug in x equals pi into our circled equation, the original one at the top. And we test it. So cosine of pi, look at your unit circle there. You'll see that the x-coordinate for the point that corresponds to x equals pi, that x-coordinate is negative 1. All right, and so we have negative 1. Negative 1 plus 1, that's 0. Now let's test sine of pi. What is the sine of pi? Well, we're going to be looking for the y-coordinate of that point, and that y-coordinate is 0, and therefore 0 equals 0, and x equals pi is a valid solution. And so I can do that same thing that I did before to try to keep track of my valid solutions. Just circle it. Now there's one more step. There's one more step, and that is that since the interval for our answers, for our solutions, was not restricted in the statement of the problem, we have to give the general solution. The general solution. And so we have x equals pi over 2 plus 2k pi, or x equals pi plus 2k pi. So this is the general solution for the original trigonometric equation. Let's look at another example. Root 2 secant x equals tan x minus 1. Okay, so it's just root 2, which is simply a constant, times secant x equals tan x minus 1. Now, I'm going to give you the same hint that I gave on the last screen, and that is you're going to want to square both sides and then check each solution in the original equation. But for practice, I'm going to let you do everything now on your own. So you're going to pause the video, try to do this on your own using the same strategy. Of course, it's not going to be exactly the same as the last problem, but it's the same general strategy. And then resume the video once you have your answer. All right, so going through the solution now, when we square both sides, we end up with 2 secant squared x equals tan squared x minus 2 tan x plus 1. Then we use our Pythagorean identity, which is that 1 plus tangent squared x equals secant squared x. So we put that in for secant squared x. Then we distribute the 2, and we have 2 plus 2 tan squared x equals tan squared x minus 2 tan x plus 1. And now we combine like terms, and we end up with tan squared x plus 2 tan x plus 1 equals 0. Now, remember that when you have a quadratic equation with 0 on the right side, you try to factor. But notice that when you factor this guy, you end up just with tan x plus 1 times tan x plus 1, and that's the same as tan x plus 1 squared. So we have tan x plus 1 squared equals 0. That, of course, is the same as tan x plus 1 equals 0. And that is the same as tan x equals negative 1. All right, then you want to look at that unit circle again and see where your tangent is negative 1. Now, remember that on the unit circle, tangent is sine over cosine, so y-coordinate over x-coordinate. The y-coordinate divided by the x-coordinate will give you tangent. And so that means that at points where the y-coordinate has the same absolute value as the x-coordinate, that you're going to end up with the ratio of 1, because anything over itself is 1. But look for the place where that is negative 1. That's where the numerator is positive and the denominator is negative, or the numerator is negative and the denominator is positive. And that only happens in two places on the unit circle, these two places, 3 pi over 4 and 7 pi over 4. If you look at 3 pi over 4, you'll see that you have a negative x-coordinate and a positive y-coordinate. So y over x will be negative 1. And you in 7 pi over 4, you have a positive x-coordinate and a negative y-coordinate. And likewise, y over x will be negative 1. So these are our candidates. Now, before we find the general solution, we have to test. So let's put 3 pi over 4 into our original solution, original equation, sorry. So I'm going to circle that original equation here at the top. And I'm going to put 3 pi over 4 in for x. We'll test that. All right, well, what is the secant of 3 pi over 4? You know that secant is just 1 over cosine. So first figure out, well, what is the cosine of 3 pi over 4? And you'll see that the cosine of 3 pi over 4 is negative root 2 over 2. And so 1 over negative root 2 over 2 is the same as negative 2 over root 2. And negative 2 over root 2 times root 2 just gives me negative 2. All right, so continuing our test, I found out simply that the left-hand side, when I plug in 3 pi over 4 for x, ends up giving me negative 2. Does that happen on the right? Well, what is the tangent of 3 pi over 4? The tangent of 3 pi over 4 is negative 1. Can you get that on the unit circle? Negative 1 minus 1 is negative 2. Negative 2 equals negative 2, and therefore this solution of x equals 3 pi over 4 is valid. Now let's try 7 pi over 4. First, let's get the secant of 7 pi over 4, and of course, to find that out, we look at the cosine. The cosine of 7 pi over 4 is positive root 2 over 2. It's just root 2 over 2. And then that means that the secant is going to be 2 over root 2. Just flip it. Root 2 times 2 over root 2 just gives me positive 2. But when I put 7 pi over 4 into the right side of that original equation, I have tan 7 pi over 4. That's negative 1. And negative 1 minus 1 is negative 2. And obviously 2 does not equal negative 2. Therefore, I put a big fat X, big fat red X, through 7 pi over 4 because it's an extraneous solution. It's extraneous, and that means that even though it looked good, it's invalid when you test it in the original. Last step, finding that general form. So the general solution is x equals 3 pi over 4 plus 2k pi. Let's look at this example. Find all solutions of cosine to the 4th power 2 theta. Now, of course, you know that this just means the cosine of 2 theta and then that whole thing to the 4th power. Just as you know, the squared, cosine squared theta, same thing. So don't let the 4 intimidate you. It's the same exact procedure that you'd use as if it were cosine squared, except that you're multiplying it by itself 4 times instead of 2. So this is the equation, cosine to the fourth power 2 theta equals 9/16. So here's the hint that you probably figured it out on your own, but just in case, you take the fourth root of both sides to obtain cosine 2 theta equals plus or minus root 3 over 2. Now, here's the thing that is a little bit different about this example, and you probably thought of it, 2 theta. This isn't just theta, this is 2 theta. And the best way to proceed with these is think of 2 theta as just a variable. You want to call it u, you want to call it x, y, z, p, I don't care, but consider 2 theta as just a variable. Well, you want to solve for 2 theta first, and then once you do that, then you can solve for theta. All right, so don't worry about the 2 until the end. That's the main strategy. All right, we took the fourth root of both sides to obtain cosine 2 theta equals plus or minus root 3 over 2. And you can quickly verify that if you want on your unit circles. You'll see that that x-coordinate of root 3 over 2 is at 4 different points on the unit circle. Let's see where those 4 points are. Okay, so you look at your unit circle, and you're going to see that it's at these 4 points. Okay, and you can verify this. You have an x-coordinate of root 3 over 2 at pi over 6. You have an x-coordinate of negative root 3 over 2 at 5 pi over 6. You have an x-coordinate of negative root 3 over 2 at 7 pi over 6. And you have an x-coordinate of root 3 over 2 at 11 pi over 6. All right, so basically what it comes down to, if we're just thinking of 2 theta as a unit, and we're not worrying about the 2 yet, but just treating 2 theta as its own angle, then the unit circle will tell us that the solutions for 2 theta are pi over 6 plus k pi, 5 pi over 6 plus k pi. Okay, so if you look at this pi over 6, for example, which I'm tracing now with the mouse arrow, it's obvious that the cosine of this angle is root 3 over 2. I can just read it off the unit circle. But what I have to remember is that negative root 3 over 2 is also a valid solution. And if I simply go pi units away from the pi over 6, that's what this red arc here indicates, is that I'm going pi units away from pi over 6. I end up at 7 pi over 6, and that's a valid solution. Also, if I go to this 5 pi over 6 angle, which has an x-coordinate of negative root 3 over 2, and then I go pi units away from it, I end up at 11 pi over 6, and that's also a valid solution. And so that's the pattern. I've got pi over 6 plus k pi, or 5 pi over 6 plus k pi. Now, this is what we have found as solutions for 2 theta. Not for theta yet. We've just found these as solutions for 2 theta. Now let's worry about the 2. What are we going to do? Well, the good news is you can do just as you would in algebra. And if you want to get rid of the 2, you just divide both sides by 2. When you do that, this is what you end up with. Theta equals pi over 12 plus k pi over 2, or 5 pi over 12 plus k pi over 2. And you can see that we simply divided both sides by 2. Or if you like, if it's easier for you to think of it this way, you multiplied both sides by 1/2. And so pi over 6 times 1/2 is pi over 12. K pi times 1/2 is k pi over 2. 5 pi over 6 times 1/2 is 5 pi over 12. K pi times 1/2 is k pi over 2. So this is the answer. The main thing that has been introduced now in this screen is that you need to solve for whatever's in the parentheses first, and then worry about the coefficient of the angle. All right, these are some examples that that you can handle doing on your own. So here's the first one: 3 tan x over 2 plus 3 equals 0. Now, x over 2 is the same thing as 1/2 x. It's just a different way of thinking of it. It's the same thing. 3 tan 1/2 x plus 3 equals 0. All right, so using the strategy of the last screen, where you're treating x over 2 as a unit, you're treating it as an angle, and then later worrying about the coefficient, which in this case is 1/2. All right, what I like to do is use that same strategy and proceed, and then, after you've tried it, then you can resume. All right, so this is what we have. We have 3 times tan x over 2 plus 1. We simply factored out the 3. And since we factored out the 3 and we have 0 on the right side, we just divide both sides by 3 and we end up with tan x over 2 plus 1 equals 0, and that of course simplifies to tan x over 2 equals -1. And now what we can see is that x over 2, since we're just treating x over 2 as a unit, there are tangents -1 at 3 pi over 4 and 7 pi over 4. And you can read that straight off the unit circle. The tangent is -1 at the angle 3 pi over 4 and at the angle 7 pi over 4, because the y-coordinate over the x-coordinate gives us -1. And now if we want to express this generally, we can just say 3 pi over 4 plus k pi. Now, you might ask, well, where did the 7 pi over 4 go? The 7 pi over 4 is included in this general expression. Okay, let's prove that to ourselves by putting in different values of k. Let's put in k equals 0. Well, then I just end up with 3 pi over 4, right? It's 3 pi over 4 plus 0 is just 3 pi over 4. Let's put in k equals 1. If we put in k equals 1, I get 3 pi over 4 plus pi. And 3 pi over 4 plus pi is the same as 3 pi over 4 plus 4 pi over 4. And that equals, of course, 7 pi over 4. So that's how the 7 pi over 4 is included in the general solution. Now, let's say I put in 2 for k. Then I would have 3 pi over 4 plus 2 pi. And that, of course, just brings me right back to where I started at 3 pi over 4. Okay, the last step then. The last step is if x over 2 equals 3 pi over 4 plus k pi, which we just found as the general solution, then x equals 3 pi over 2 plus 2k pi. All we did is multiplied both sides by 2 to get rid of the 1/2, and I end up with 3 pi over 2 plus 2k pi. All right, here's another example that you can work on by yourself. Sine 2x minus root 3 over 2 equals 0. All right, pause the video, try to do this on your own, and then resume when you have an answer. Going through the solution, we have sine 2x equals root 3 over 2. 2x equals pi over 3 plus 2k pi. 2 pi over 3 plus 2k pi. You get that straight off your unit circle. If you look at pi over 3, you'll see that it has a y-coordinate, root 3 over 2. So the sine is root 3 over 2. If you look at 2 pi over 3, you will also see that the sine, or the y-coordinate, is root 3 over 2. And then the 2k pi makes it a general solution. Last step then, to get rid of that 2 that's in front of the x, is to multiply both sides by 1/2. And we end up with x equals pi over 6 plus k pi. Or 2 pi over 6 plus k pi. And since 2 pi over 6 is simplifiable, our final answer is x equals pi over 6 plus k pi, or pi over 3 plus k pi. Here's the classwork, page 396. Please write these numbers down and see you in class.